So this video is going to cover our last two topics. We're going to talk about linear dependence and independence and explore that idea a little bit more, and then move into eigenvectors and eigenvalues. So we know that the solution of a linear system is a set of numbers. We're solving for our unknowns. And it turns out we don't care what our unknowns are called. All we need are the numbers. That's why we have our augmented matrix, where we just keep track of all the values in A, all of our coefficients, and all of the values in B, all of our constants from our right-hand side. So when we have a system of equations, we're going to have one of three options. We're going to have a consistent system or an inconsistent system. A consistent system is going to have one or an infinite number of solutions, and an inconsistent system is going to have no solutions. So here's what it looks like graphically. So here's our equations. So this is if we have the rows of our matrix. And here's what it looks like in vectors. So here's we have the columns of our matrix, of our augmented matrix specifically. So, and this is two equations, two unknowns. So we can either have one solution with a consistent system. So that's where we have one intersection point. We have one solution. Or we can have an infinite number solution. So this is also a consistent system, but infinite number solutions is if they're the same line. So once again, these are independent vectors, or independent equations. These are dependent equations, because it's the same line, it's the same information. And then lastly, we can have an inconsistent system with no solutions. These are conflicting equations. From a vector perspective, it might look like this, where this is our column 1, column 2, and this is our B vector. So the green would be our B vector. So here's what it looks like to have a consistent system with one solution. Our two columns are independent of each other. They're not the same line. They're not collinear. And our B vector is separate from both of them. So I can go ahead and multiply this by a certain number, multiply this by a certain number, and when I add them together, I get to my B vector. For a consistent system with infinite solutions, it's all the same vector. There's no new information. Column 1 and column 2 are the same information, and that B vector also exists in the same line. They are all collinear. I probably spelled that wrong. I think 2 L's. The other option is inconsistent system with no solution. So that happens if our column 1 and column 2 are the same line, but our B vector is not in that same space. Our B vector does not exist with our vectors of our A matrix. So B is not in the same space. It's not collinear. It's conflicting information. Okay, so here's that summarized. If the vectors are non-parallel and non-collinear, then the system is consistent and has one solution. If they're all parallel, including the B vector, then the system is consistent with an infinite number of solutions. And then if they are parallel but not on the same line, and the B vector is not in the same space, or not on the same line, not collinear, then the system is inconsistent with no solution. Okay, so all of this depends on whether or not our equations, whether or not our vectors are linearly independent, which means they are separate pieces of information, they are not conflicting, they are not on the same line. So that is our key thing to figuring out which situation we have. So we're going to use 3 different methods in order to determine whether or not vectors are linearly dependent or independent. We've already been introduced to one of them, and that's using this idea of a linear combination, where if vectors are combinations of each other, if you have a scalar times a vector plus a scalar times a vector plus a scalar times a vector, etc., and we solve for these constants, these unknowns, solve for C1, C2, etc. So we set up the vectors as a linear combination like we did in week A. We solve for our constants. If our constants are all 0, then the vectors are linearly independent. But if we have at least one that is not 0, then my vectors are dependent. And we also introduced this theorem that says that if we have more vectors than the space they live in, so if we have 5 vectors in R3, they are automatically linearly dependent. So 5 is greater than 3. So that's our first method. Our second method is to find the rank of a matrix. The rank of a matrix is the maximum number of linearly independent rows or columns. Okay? The matrix can be any size. But what we're going to do is if we have a matrix, we can reduce it to REF. So remember, get our lower triangle of zeros. And the matrix can be any size. It really doesn't matter. But get a lower triangle of zeros. Reduce it to REF. What happens is sometimes we have 0 rows that show up at the bottom. And we saw this when we were solving systems of equations with Gauss elimination. So the number of non-zero rows that we have after REF is found, is the number of linearly independent rows or columns, doesn't matter, in the matrix. So if I have a matrix set up like this, and when I get to REF, these ones go to 0 and these ones go to 0, then I only have 2 linearly independent vectors. And that's how that works. So if we want to find the rank of a matrix, we go ahead, create a matrix with the vectors. They can be rows or columns, doesn't matter. It's the same answer either way. We reduce it to REF, and then figure out how many non-zero rows we have. So anything, so even if I have one number here that's not 0, it is not 0. And so the rank is equal to the number of non-zero rows. That's the number of linearly independent vectors. So if I have 0 non-zero rows, so if I don't have any 0 rows, then my vectors are all linearly independent. However, if I do have 0 rows that show up, my vectors are linearly dependent. And we saw this with our systems of equations, where sometimes we had a full system that shows up like this. That means we have the rank of A. So if we look at this half, the rank of A, there's 3 non-zero rows. If we look at the rank of AB, there's still 3 non-zero rows. However, sometimes we also had zeros that showed up on the bottom. So the rank of A, this side, would be 2. The rank of AB, both sides would also be 2. And then lastly, we also had this situation where we had zeros that only showed up on the A side and not on the B side. So the rank of A here is 2 and the rank of AB is 3. Okay, so depending on what situation we have, we can determine whether or not the system is consistent with one solution. If the rank is the same on both sides and it's a full rank, meaning it has the same number of rows as the matrix. Or the system is consistent with infinite solutions where we have 0 all the way across. Or it's an inconsistent system with no solutions if the rank is not the same. Okay, and we will explore that in class. Okay, so that's 2 methods to find linear independence. The last method to find linear independence is by using the determinant of a matrix. So if A is a square matrix, keep that in mind. Determinants can only be found of square matrices. Then the column vectors of A are linearly independent if and only if the determinant of A isn't equal to 0. If the determinant isn't equal to 0, that means A inverse exists. So it turns out A inverse exists only if my vectors are linearly independent, which means my determinant is not equal to 0. Okay, so determinant is another way to determine whether or not our vectors are linearly dependent or independent. And fundamentally, all this whole idea comes down into these summary statements, where it says, if we have a matrix, and notice it's a square matrix, these statements are equivalent. The vectors of A are linearly independent. The vectors of A, or the rows of A, are linearly independent. So note, rows, columns, same thing. If they're independent, that means my determinant is not equal to 0. If my determinant isn't equal to 0, then my matrix is invertible. If my matrix is invertible, that means I have a unique solution and a consistent system. And it doesn't matter what my B vector is. For every B vector, B can be whatever. If A is invertible, I have a unique solution. It also means the rank of A equals the rank of AB, and that's a full rank. So equals n means it's a full rank, equal to the number of rows or equations. And then if I have a homogeneous system, so a homogeneous system is where my B vector is 0. And if I have a homogeneous system, then my only solution is the trivial solution, where x equals 0. This should be x vector. where x equals 0. So all those are equivalent. So if I tell you that the vectors of A are linearly independent, you should be able to determine all of this information. Which means if the vectors of A are linearly dependent, doesn't matter if they're rows or columns, that means my determinant equals 0. That means my matrix is not invertible. A inverse does not exist. A is singular. And I'm going to have one of two options. Either my system is consistent with an infinite number of solutions, so these two go together, or it's going to be inconsistent with no solutions, so these two go together. And the way I can determine that is based on the rank. So I would have to do Gauss elimination in order to figure out which one I have. And then if I have a homogeneous system, so if B equals 0, then it's automatically going to be consistent, and I'm going to have an infinite number of solutions. So I've summarized this in this little graphic down here. Here's a B vector equals 0. It's a homogeneous system. It's always consistent. If I have a unique solution, then that solution is going to be 0. I have a full rank, and my determinant isn't equal to 0. If I don't have a unique solution, then I have an infinite number of solutions, and my determinant equals 0. If I don't have a homogeneous system, then I've got a couple more options. It's either going to be inconsistent with no solution, and my determinant equals 0. Not always the case, though. Or I'm going to have a consistent system where my ranks are equal to each other. It's either going to be a unique solution where determinant of A is not 0, or it's going to be infinite solutions where a determinant is equal to 0. Okay, so we've got this graphic that kind of summarizes those statements above. So whether or not our vectors are linearly dependent or independent is super important in terms of which area we are going to end up in. Okay, last topic, eigenvalues and eigenvectors. So thus far, we've been working with AX equals B. Okay, now we're going to change this side, where when we do A times a matrix, or times a vector, essentially what we're doing is we're moving that vector in space. We're saying, okay, transform X by multiplying by a vector to move it somewhere else in space. Sometimes, though, there are vectors where when we multiply by a matrix, it doesn't move in space, it just moves in the same line. So if I take X and I multiply it by a matrix, it just appears to have been scaled. Okay, where it shifts somewhere along this same line. So now instead of it being B, we're interested in terms of which vectors stay on that line. Okay, so the problem of solving AX equals lambda x, lambda being a scalar, and x being this vector, for the non-zero vector x is called the eigenvalue problem, and you saw them in your project. So some vectors, when multiplied by A, are just appears if they're multiplied by a constant. So we want to figure out how to find these eigenvectors and how to find these eigenvalues being those scalars. So the way we do that is we go ahead and rearrange this, where AX minus lambda I. Just move this to the other side, equals 0. I'm going to factor out an A, or factor out X, so it becomes A minus lambda identity, because lambda is a scalar, so I need to adjust it. So multiplied by identity, X equals 0. This is where I'm interested. This is going to tell me how to solve for these X values and these lambdas. Okay, so note, this is a homogeneous system, and we just talked about how a homogeneous system, where it's either going to be a unique solution where that solution is X equals 0, or we're going to have an infinite number of solutions. And this one's not terribly interesting to us. We don't care about where X equals 0 all the time. This one, however, an infinite number of solutions, is interesting. So we're going to go ahead and force this problem to have an infinite number of solutions. And the way we do that is by forcing our determinant to equal 0. Okay. So this one's not interesting. This one's interesting. Okay, so we're going to force it to be determinant to be equal 0. That's going to give us our eigenvalues. So the determinant of this is our new A x equals B. We're going to say A minus lambda I equals 0. The determinant of A minus lambda I equals 0. This is called the characteristic equation, and this is how we can find our eigenvalues. So we just solve for it. Set it up, solve for it, move on. We can also check our answers in MATLAB. The Eig function can also solve that for us, but we will also do it on paper. Okay, so now that we've forced the determinant to be equal to 0, that means we've forced it to have an infinite number of solutions, and we want to start figuring out what these solutions are. So to figure out what these solutions are, what x's are, we can go ahead and plug in each lambda value to our original equation there and solve for x. So plug in each lambda. Note each lambda is going to give us an infinite number of solutions, so we're going to use Gauss-Jordan elimination. Otherwise, it's not really going to work. We can't use a lot of our other methods because we need a unique solution for those. But Gauss-Jordan elimination we can use regardless of how many equations we have or how many solutions we're going to get. So we're going to use Gauss-Jordan elimination, and we're going to solve for our x values. Okay, so here's our process for solving eigenvalue and eigenvector problems. Solve the characteristic equation for lambdas. You will have multiple lambdas. So just keep that in mind. It's not just one lambda value. It's multiple, depending on how big your matrix is. A 2 by 2 has 2. A 3 by 3 has 3. A 4 by 4 has 4, etc. And then we're going to solve that many systems of equations. So plug in each lambda value into this equation and solve for x. So one of the benefits of eigenvalues and eigenvectors is this idea of diagonalization, where we can uncouple a linear system. There's lots of applications of doing this. I'm going to tell you how to diagonalize a matrix. We're not really going to jump into the applications, but there's lots of applications. Here's a list of some of them: solving differential equations, which you will see if you haven't already seen in DiffEQ, material deformation, dynamic systems, signal image processing, principal component analysis, numerical methods, control systems, pattern recognition. There's lots of applications for this. This is beyond the scope of this course. A lot of these are upper level courses, so you might see them later on in your program. But we're just going to focus on literally the mechanics of doing this problem. So eigenvectors and eigenvalues can be used to diagonalize or uncouple a linear system. So they can be used to help solve systems, kind of like factorization. It's like a special additional form of factorization. Okay, so a matrix can be diagonalizable, not always, but it can be diagonalizable if it has n linearly independent eigenvectors. It's going to have n independent eigenvectors if it has n distinct eigenvalues. So if all the eigenvalues are unique, then it's going to have independent eigenvectors, which means we can diagonalize the matrix. The diagonalization can be written as x inverse times A, x equals, this is capital lambda. So this is capital lambda. So keep that in mind. Where x is the matrix of eigenvectors. So just like you saw in your project, x looks like this, where column 1 is the first eigenvector, column 2 is the second eigenvector, column 3 is the third eigenvector, etc. This lambda here, capital lambda, is that diagonal matrix that you had in your project, where the lambdas are on the diagonal. And then this is x inverse, and then this is just A. So those, A comes from your system equations, and x inverse comes from the inverse of A, or the inverse of x. Once we find all those pieces, then we can set up our diagonalization. So we need to find the eigenvalues. That'll give us this matrix. That'll give us capital lambda. We need to find our eigenvectors. That'll give us this matrix. That'll give us x. We need to find, we plug those in to get lambda and x respectively, and then we can find the inverse of x and put everything together.